Okay, Assalamualaikum warahmatullahi wabarakatuh and good morning. Okay, so as you all know, starting from 4th of May 2020 until the end of the semester, we will have our lecture fully online. So this will include your lecture, quizzes, midterm tests, and also your final exam. Okay, so just a reminder, for this subject, communication system, you will have two quizzes. Okay, so the first quiz, I will put it online inside ULearn. So it will cover chapter 2, which is amplitude modulation. Okay, and then we will have another quiz. I'm not sure yet what chapter that it will cover. Okay, so and then so your quiz, I will do it maybe next week or the following week. Okay, and then your midterm test, I haven't decided the exact date yet, but it will cover chapter 1 and also chapter 2. Okay, introduction to communication system and also angle modulation, amplitude modulation. So so I think for quiz 1 and also your midterm test, there will be no problem because we have finished the syllabus before the PKP started. Okay, so basically today we will start with a new chapter, which is chapter 3, angle modulation, transmission and reception. Okay, so in the previous chapter, you have learned what is modulation. Okay, so that is very important for you to know the definition and the process of modulation. And then there are several types of modulation techniques. Okay, we have amplitude modulation, we have angle modulation, and also we have digital modulation. Okay, so three modulation techniques. So amplitude modulation already been covered in chapter 2. Angle modulation will be covered in chapter 3, and digital modulation will be covered in chapter 4. Okay, for angle modulation, okay, it can be further divided into two, which is frequency modulation and phase modulation. Okay, so I will explain this further later on. Okay, so today we will cover chapter 3, part 1. So these are the sub-chapters for chapter 3. So chapter 3 part 1 will cover up until 3.4 modulation index and two-stand modulation. Okay, so this is what I've told you before, that there are two forms of angle modulation. The first one is frequency modulation, and the second one is phase modulation. Okay, and angle modulation is in general is better than the amplitude modulation. Okay, however, it still has several disadvantages. Okay, so the advantages of amplitude modulation compared to amplitude modulation is that in terms of noise rejection, meaning it has lower noise compared to amplitude modulation. Okay, when we talk about AM is referring to amplitude modulation. It's not referring to angle modulation. Okay, for angle modulation, we usually refer to as FM or PM. Okay, so AM here is the amplitude modulation. Okay, so this is the first advantages, noise reduction. It has a lower noise compared to amplitude modulation. It has improved system fidelity. So what is fidelity? You have learned the definition of fidelity in chapter 1, if I'm not mistaken. So basically, fidelity is the ability of a system to replicate the original signal. Okay, meaning output equals to input. Okay, and so means that this, if you have improved system fidelity, it means that you have improved accuracy and more efficient use of power. So this means that it uses less power compared to amplitude modulation. However, it still has several disadvantages compared to amplitude modulation. So the first one, it uses wider bandwidth, okay, and then it utilizes a more complex circuit. So you need to know that when you deals with the more complex circuit, automatically you will deals with a higher cost. Okay, the more complex the circuit, the higher the cost will be. Okay. So this angle modulation is used extensively for commercial radio broadcasting, television sound transmission, radio, microwave, and satellite communication. So basically what I can say is that angle modulation is widely used compared to amplitude modulation. Okay. So next, introduction to angle modulation. So stated here is that angle modulation is the result whenever the phase angle of a sinusoidal wave is varied with respect to time. Okay, so this is the equation for angle modulated wave. For the output of the angle modulation, we define it as MT. Okay, so MT equals to VC cos omega CT plus theta T. Okay, where VC is the carrier amplitude, omega C is the carrier frequency, and theta T is the instantaneous phase deviation. And you can see that over here, theta T is given by FVM sine omega MT, where omega m is the modulating signal radiant frequency and Vm is the peak amplitude of the modulating signal frequency. So basically, angle modulation and amplitude modulation is quite similar. You have two input, one output. So the two input is carrier frequency. The second one is modulating frequency. If you remember, carrier frequency is a high frequency signal. Modulating carrier signal is a high frequency signal that we generate, and modulating signal is the signal that we want to transfer. Okay, so modulating signal is usually lower frequency compared to carrier frequency. So this is the same as angle modulation. You have two input, carrier and also modulating signal. Okay, the difference is the result of the output. Okay, so if you refer to your notes in chapter 2, okay, so basically the concept is similar. This is amplitude modulation. You have two input, carrier signal VC and the modulating signal VM, and you have the output. It's just that the signal for the output is different compared to the angle modulation. Okay, so and then if you look at here, this is in chapter 2. So if you look at here, this is the equation for amplitude modulated signal, VAMT, the output of the amplitude modulation. So we present it as VAMT equals to EC plus MEC sine 2 pi FMT sine 2 pi FCT. Okay. And then you compare this with the output for the angle modulated, okay, which is this one. The concept is the same. You have two inputs. Now the output, this is the output for angle modulation. This is the output for amplitude modulation. Okay, So if you can see, the difference is basically, if you look at here for the angle modulation, the amplitude is constant. The amplitude is always equals to Vc. But if you look into the frequency content here, the frequency content here is actually affected by the modulating signal, which is Vm sine omega mt, because theta t is equals to Fbm sine omega mt. So basically, the amplitude of the angle modulation is fixed, but the one that is varying according to the modulating signal is the phase and the frequency. But for this one, if you look at here, for the amplitude modulation, the the amplitude here is varies, okay, depending on the modulating signal, okay, and also the modulation index. So the input here is actually EC plus MEC, okay, and so the difference between basically that is the difference between angle modulation and amplitude modulation. So angle modulation, the output, the frequency content of the output is affected by the modulating signal. For amplitude modulation, the amplitude of the modulated signal is affected by the modulating signal. Okay. So, like I explained before, angle modulation consists of frequency modulation and also phase modulation. But what is the difference between FM and also PM? So stated here, FM is the results when the frequency of the carrier is varied directly by the modulating signal. Phase modulation is when the phase of the carrier is varied directly by the modulating signal. Okay, so it's different. Frequency and phase is different. So first, let's look into frequency modulation. You can see that over here, for FM, the frequency variation is directly proportional to the amplitude of the modulating signal. So this is what I explained before. For angle modulation, specifically the frequency modulation, the frequency variation is affected by the modulating signal. It's directly proportional to the amplitude of the modulating signal. For phase modulation, the phase variation is directly proportional to the amplitude of the modulating signal. So if you look at here, this is the angle modulation representation in frequency domain. Okay, so this is in frequency domain, or we can call it as frequency spectrum. So if you remember in the chapter 2, okay, we just look at this part. This is the frequency domain. The signal in terms of frequency. Okay, so we have the middle frequency is FC, similar to amplitude modulation. And then over here we have FC plus delta F and FC minus delta F. But for amplitude modulation, if you remember, the middle frequency is FC, but the upper side frequency is FC plus FM, lower side frequency is FC minus FM. So it's different, okay, for amplitude and angle modulation. Okay, so you just look at this part. This is the frequency domain. Okay, the one in the bottom is just to show you the effects when the modulating signal varies. Okay, so stated here, the carrier frequency Fc change when acted on by modulating signal, and the magnitude and direction of the frequency deviation delta F is proportional to the amplitude and polarity of the modulating signal. So if you look at here, okay, so this is your modulating signal, okay, and this is the amplitude. So the amplitude of the modulating signal is proportional to the delta F here is directly proportional to the amplitude. Okay, so what happens if you have a lower amplitude uh, modulating signal? For example, you have a modulating signal like this. So this is the amplitude. Okay, so basically delta F will be, so this is delta F. So you can see that when the amplitude of the modulating signal is higher, then the frequency deviation will be higher. If the amplitude of the modulating signal is lower, then the delta F here, the frequency deviation will be lower. Okay. This one is the angle modulation in time domain. Okay. You can see that this is in terms of time, t. Okay. When the time is varies. So the phase of the carrier is changing proportional to the amplitude of the modulating signal. The phase shift is called phase deviation or delta, delta theta. Okay. So if you look at here, so now this is this is the signal in time domain. Okay, the output signal in time domain. This is your modulating signal. So what you want to state here is that the delta theta is proportional to the amplitude of the modulating signal. Okay, so meaning if the modulating signal is amplitude is higher, then the delta theta here, this one, this is delta theta will be bigger or higher. Okay, so meaning the difference, the phase difference between the first signal and the second signal will be higher. And other than that, we can also calculate for the peak-to-peak frequency deviation. Okay, delta F peak to peak. So delta F peak to peak is 1 over T mean minus 1 over T max. T is the time taken for one cycle. Okay, time for one cycle. So T mean is from this to this. T max is from this point to this point, one cycle. Okay, so you can use this formula and you can get the peak to peak frequency deviation. So to differentiate between frequency modulation and phase modulation, there are several terms that you need to be familiar with. The first one is instantaneous phase deviation. Okay, it is the instantaneous change in the phase of the carrier at a given instant of time and represent as delta t. Okay, the unit is in radian. And then we have instantaneous phase. Instantaneous phase is the precise phase of the carrier at a given instant of time. This is the precise phase. This is the deviation. So instantaneous phase is omega ct plus delta t. And then we have instantaneous frequency deviation represented by the first derivative of the instantaneous phase deviation. Delta delta apostrophe. I call it as dash. Okay, delta theta dash t, and the unit here is reading per second because it's frequency. And then we have instantaneous frequency, which is omega c plus delta dash t. The unit is in radian per second. So from the previous four terms, okay, this four terms, okay, the phase modulation and frequency modulation can be defined as, for phase modulation, theta t is proportional to the amplitude of the modulating signal. But for frequency modulation, theta dash t is proportional to the amplitude of the modulating signal. Okay. So for a modulating signal VMT, okay, theta t can be defined as kVMT, and theta dash t equals to K1 VMT. Okay, where K and K1 are constants and are the diffraction sensitivities of the phase and frequency modulators. So remember, this is your origin, this is your modulated signal, your output. In the previous slide, you have MT equals to VC cos omega CT plus theta T. So if you put equation 8 and equation 9 into equation 1, which is this one, you will get, because in the previous slide, we know that theta T is equals to KVMT. You put it inside this equation, so you will get VC cos omega CT plus KVM cos omega MT. So this is the modulated equation, the equation for the modulated signal for PM. For frequency modulation, theta t, because theta dash t is the first derivative. Okay, so in order to get theta t, you need to integrate it. Okay, so what happens is that MT will become MT equals to VC cos omega CT plus in the integration of the first derivative theta t. Okay, and theta dash t is equals to K1 Vm cos omega mt. So you will get this equation. And lastly, if you simplify, you can get Vc cos omega ct plus K1 Vm over omega m sine omega mt. Okay. So these are the formulas that you need to remember. This one and also this one. Okay. So this is the summarized table. So you look at here, this for phase modulation, when if the modulating signal is VMT, this is the angle modulated wave, VC cos omega CT plus KVMT. For frequency modulation, if the modulating signal is VMT, VC cos omega CT plus K1 integration VMT dt. However, if the modulating signal is equals to Vm cos omega mt, it will become Tc cos omega ct plus kvm cos omega mt. And if for this one, for frequency modulation, if the modulating signal is Vm cos omega mt, so just substitute this into Vm, so you will get this equation. So this figure shows the waveform of frequency modulation and phase modulation of a sinusoidal carrier by a single frequency modulating signal. So you have three signals. So figure A, this one, this is the signal for the carrier signal. So you can see that this is high frequency signal. Okay. And figure B is the modulating signal, the signal that you want to transfer. So you know that this is the modulating signal because it has a lower frequency compared to the carrier frequency. And C is the frequency modulated wave. D is the phase modulated wave. So you can see that it's quite similar, the output for frequency modulation and phase modulation. However, the ones that is different is this part. Okay, so you can see that you can see the different frequency. Okay, this is high frequency, this is low frequency. Okay, so to explain this, okay, so from the previous figure, the maximum frequency deviation occur during the maximum positive and negative peaks of the signal. So you can see that we state that maximum frequency deviation occur during maximum positive and negative peak. So you can see that it happens at the maximum deviation happens at the positive and negative peak of the modulating signal. Okay, this is the maximum deviation. But if you compare to phase modulation, the maximum frequency deviation occurs during the zero crossing of the modulating signal. So you look at here, the maximum deviation here happens during at the zero crossing. So this is the zero crossing. So you can see that this is the maximum deviation and this is the maximum deviation. So that is the difference between frequency modulation and phase modulation. Okay, so the last part we have the modulation index and percent modulation. So same as amplitude modulation, angle modulation also have modulation index and percent modulation. However, the modulation index and percent modulation is different for frequency modulation and phase modulation. So if you look at here, if you compare equation 10 and equation 11, this one, equation 10 and also equation 11, it can be written in general form, which is mt is equals to Vc cos omega ct plus m cos omega mt, where m here is the modulation index. Okay, so first we'll look at the modulation index and percent modulation for phase modulation. So for phase modulation, the modulation index we also call as peak phase deviation or delta theta. So it is proportional to the amplitude of the modulating signal. So this is the equation for modulation index for phase modulation. M equals to delta theta equals to kVm. Okay, why kVm? Because this is actually omega ct plus m cos omega mt. So the m for phase modulation equals to kVm. So m is directly proportional to Vm, the modulating signal amplitude. So therefore, for phase modulation, the modulated waveform equation MT can be written as this is the previous one, Vc cos omega ct plus kVm cos omega mt, and then we know that kVm is equals to delta theta and delta theta is equals to m. So we can write mt equals to Vc cos omega ct plus m cos omega mt. Okay, so this is for phase modulation. Next, modulation index and percent modulation for frequency modulation. Okay, so modulation index is directly proportional to the amplitude of the modulating signal and is inversely proportional to the frequency of the modulating signal. So for different from phase modulation m equals to kVm. However, for frequency modulation, m here is equals to k1Vm omega m. Why k1Vm over omega m? Because it linked to this equation. So this is the m. So M is equals to K1 Vm over omega M. Okay, so that's why stated here, the modulation index is directly proportional to the amplitude of the modulating signal Vm, and it is inversely proportional to the frequency of the modulating signal omega M and Fm. Okay. So you can write M equals to K1 Vm over Fm. And then also for Vm, also for Fm, the peak frequency deviation or delta F is simply the product of deviation sensitivity and the peak modulating signal voltage. So delta F, stated here, delta F is actually equals to K1 Vm. So M here will become delta F over Fm. Why? Because this K1 Vm is equals to delta F. So M will become delta F over Fm. So you can also write the delta F modulation index equals to delta F over Fm. So therefore, for frequency modulation, the output signal or the modulated signal, you can write it as this one, either this one, Vc cos omega ct plus K1 Vm over Fm sine omega mt, or this one, Vc cos omega ct plus delta F over Fm sine omega mt, or this one, which is Vc cos omega ct plus m sine omega mt. Okay. So this is, you should remember the output equation mt. So 3.4.2 is the modulation index and percent modulation. We want to know the relationship between modulation index, frequency deviation, and phase deviation in respect to the modulated signal amplitude and frequency, modulation index, frequency deviation, phase deviation, and frequency deviation. So if you look at the first figure here, for both frequency modulation and phase modulation, when the amplitude of the modulating signal is increased, the modulating index will be increased. And then this one, for frequency modulation, when the modulating signal frequency increase, the modulating index will decrease. However, for phase modulation, when the modulating frequency increase, the modulating index will remain unchanged. For this one, figure C, for phase modulation, when the amplitude of the modulating signal increase, then the delta theta will increase. And then same for figure D, when the amplitude of the modulating signal increase, and then the delta F will increase. Okay, this is just to show you the relationship. Okay, how do we get this relationship based on the previous equation? Okay, so this is the summarized table for angle modulation. I'm not sure yet whether this table will be given in your final exam, but I think most probably this table will be given. Okay, so you so that it is easier for you, you don't need to remember the formula for angle modulation. But for amplitude modulation, no table will be given, no formula will be given, only for angle modulation. Because angle modulation, you have FM and also PM. So there's a lot of equation that you need to remember. So, so this one is the modulated wave output signal for FM and also PM. And then you have the diversion sensitivity equation for device here, and then this is the equation for modulation index, okay, and so on. Okay, but I'm not sure whether it will be given, but most probably it will be given in your final exam, not in your quiz. Okay. Okay, and then this is the last slide. So stated here, with angle modulation, percent modulation is the ratio of frequency deviation actually produced to the maximum frequency deviation allowed. So the percent modulation, okay, this is to calculate percent modulation, equals to delta F actual value divided by delta F maximum multiply with 100%. Okay, so this is the formula for percent modulation. Okay, so basically that's the end for chapter 2, chapter 3, part 1. So if you have any questions, you can directly ask me personally through Yulen or through Telegram group or personally WhatsApp me. Okay. Um, so I think that's the end for this online lecture for today. So later on, okay, for each online lecture, we will have a pre-recorded video. However, for the tutorial session, we will have a live streaming session. Okay. Okay, so thank you.